Alright, so with this video we're going to use the simulation results that you just got by following the last video, and we're going to do a consistency check. This is always good to do a check whenever you're doing a simulation, just to make for sure that everything worked out the way you think it should have. So we're going to check the pin where we have the highest forces. So we need to kind of look through and see where our largest forces are. It looks like our largest force is this 83.33 newtons that are in compression. Let's see if the other forces are also fairly large, and let's see whether pin 5 or pin 4 seems to have the larger ones. So we've got 83 here, we've got 50 here on pin 5. Now we've got 83, 67 here, and minus 50. So it looks like pin 4 is our winner. So pin 4 is our location that we want to draw our free body diagram and do our analysis on. So let's document this as pin 4. Also, if you drew a diagram in the previous video, we call that pin F. So I'm just going to also say this guy is also pin F. And with our free body diagram, so a little circle that I drew, everything that I cut through with the circle, I need to show that as a force. So I've got pin 4 here. I cut through this 50 over here, so I need to show that. I cut through this 66.67, so I need to show that. And then I cut through this negative 83, so I need to show that. And there's kind of two approaches to this. One would be to just show everything is coming out and then literally put in a negative number. That sometimes kind of looks kind of strange, though. It'll work and it'll give you the correct answer. So what I'm going to do instead of doing this is I'm just going to flip the arrow, and then I'm going to use a positive number because I have made the allowance for this being negative by the direction of the arrow here. And I'm going to do the same thing over here. And let me put in my 66.67. I need to also grab any distance information. I've got that on my diagram just right up here. So the idea is that going along from F to D, I'm going up 4 feet and I'm coming over 3 feet. So I can draw that on this force here. It's going to be over 3, up 4. So this is a little similar triangle that goes on the force. We can also calculate its hypotenuse. Let me scoot this 83 over just a little bit. So the hypotenuse here is going to be 3 squared plus 4 squared, add them together, take a square root, and that's going to give us a 5. So you could use this information to go back and get an angle, or we can use it directly just as a fraction. So I'll show you both methods. So if you wanted to get an angle, let me draw it over here because I don't want to make my diagram too cluttered. That would be this angle theta. So we could say that this angle theta is equal to the inverse tangent of the 4 side, because we're doing distances, not forces right now, divided by the 3 side. So 4 divided by 3, and then do inverse tangent. And that gives us a 53.13 degrees. And then you could later, when you need them, you could get a sine and cosine. So let's see what we'd get if we did sine. And we get 0.8. That's kind of interesting. Let's try 53.13 and do cosine. and we get 0.6. That's also this fraction over here, strangely enough. So remember that cosine is the side that's adjacent over the hypotenuse. So that's actually just the same 3/5 that you have on the similar triangle. And for sine, it's the opposite over the hypotenuse. So it would be the 4 over the 5. So again, you can do this either way. You can get an angle and go back and use it that way, or you can just use the fractions, the 3/5 and the 4/5. The angle method might be a little more general. I specifically used a 3, 4, 5 right triangle for this one just to show you this trick. If you just picked an angle or used 45 degrees or something like that, you might prefer to use the angle. So now we're going to do our equations. So we're going to do this symbol that's a capital Greek sigma. It's kind of like a Greek S. It just means add up. And then we're going to use this to say all the forces in the x direction. So let's see what we get. So when we add these up, we're going to use this regular old sign convention that this direction is positive x, this direction's minus x, this direction's positive y, and this direction is minus y. So our 50 Newton force is going in the positive x. So just put a positive sign, or just don't leave a sign to make it positive. Our 66.67 is not going in x at all, it's going only in y, so we just leave it out. And then with this one, it's the 3 side that's parallel to the x, so this would be 3/5 of the force. And then we go back and look at our diagram. Looks like this one's pushing on it in this negative x direction, so it's negative. Remember that the 3/5 is the same as cosine of theta. So let's do 50 minus 3 divided by 5 times 83.33. And we get 0.002 newtons. So this is within round off of being equal to, I'm going to put an approximately equal to 0. And it's going to put a little slash through it to make it clear that it's a 0 newtons. And that's what we're trying to check for. If everything's working on the simulation, then this system is in static equilibrium. That means it's not going to be accelerating in the x direction or the y direction. And in order for that to be true, then the forces in the x direction all have to cancel each other out. Otherwise, from Newton's law, you'd have the old F is equal to mass times the acceleration, and that means that pin would be moving somewhere. Okay, so this is a check, so I'm going to put a check mark next to that. So we pass this one. Now let's look at our sum of forces in the y direction and see what we get. So 50 only went in the x, so we don't show it. 66.67 looks like it's going in the negative y, so it gets a negative sign. And then the 83.33 looks like it's going up in the positive y, so it gets a positive sign. And we're going to do the 4/5. Remember, this is the same as sine of theta. And I got negative 0.006 newtons. And so we're going to say that that's close enough to be in 0. And so that also checked. So we passed the 2 tests that we were using for consistency. We got that the sum of forces in the x direction was equal to 0, and the sum of forces in the y direction is equal to 0. If you get a different answer, make for sure that the truss that you drew in the simulation tool actually matched the angles that you used or the distances that you used up here. That's kind of the most common error for the consistency check not quite matching, is having an angle up here that you think you've got 20 degrees, but then when you draw it down here you don't quite have 20 degrees. Maybe you have 25 degrees or something like that. Then you'll see that these will be significantly different than 0. Make for sure with this lab that you just pick the one value the one pin where you have those highest forces. We just want to look at that one pin where it looks like it would be the most likely failure condition. And then when you test your wooden trusses or whatever you were able to make them out of, see if that's where you failed. Did you fail at pin 4? Or maybe did you fail between pin 4 and pin 5 due to that really high compression force? Usually if you're using kind of flexible members, the compression force, they're a little more sensitive to that compression force and they'll fail in a buckling. They'll just kind of fold in on each other. Usually if you have flexible members, they're fairly strong in tension, usually much stronger in tension than they are in compression. So, thanks for watching.